Okay, hi. Um, we have finished Ismail's help with the exam grading, but I haven't double checked, and I would like to double check everything before I post them. So I'm holding back for a couple of days. Maybe by Tuesday they'll be posted. But we finished grading, and I believe the average was 70. So. And there were, a couple of 98s. So obviously some people did very well. There's obviously also some, unfortunately, not obviously, unfortunately some low grades too. So I want to, double confirm things. Anyway, today I'm going to do I'm going to do an example of a 2 degree of freedom, not 2 degree of freedom, indeterminate to the second degree. It's going to take quite a bit of computation, even though none of it is particularly difficult, but it will take a lot. So there's going to be a lot of erasing and putting back and erasing and putting back. In addition to that, I'm going to try to teach you a couple of details with regards to managing equations so that you don't have to substitute numbers if you don't want to until the end and things like that. And so as far as the homework goes, your next homework is to repeat this example that I'm going to do today in extra clean form. It's going to take 7, 8, 9 pages if you do it clean, maybe 10. So I'd like you to do it, with a straight ruler and write everything very clean and have it as an example that you can keep for your files. And needless to say, it's not a question of taking the view of the lecture and copying what I was doing, because who knows, maybe I'll just have an error multiplying here somewhere. I don't know. I try not to make an error, but I can't be 100% sure. So you can use the video to guide your computations and everything, but you should confirm independently that you agree with every step that is being taken. Okay? All right. So here we go. The structure that we will consider see, yeah, it's doubly fixed on the left support and on the right support, and it has a hinge in the middle. The height of the columns, let's use one dimension L. Let's say that the height is 0.5 L. The distance to the hinge from this side is L, and this other distance is also L. If we need to refer to points, that will be A, B, C, D, and E. Okay? Now, how indeterminate is this structure? The way to think about it is, if there was no hinge, right? If there was no hinge, this would be indeterminate to the third degree, which you can get by either eliminating the support and seeing that you just have a bent cantilever. But if you want to use the idea of the open tree, you could just cut it open through the middle and see two independent trees. So since you made one cut, that would be indeterminate to the third degree. However, because we have imposed a condition that this moment at this point is 0, then we know one thing about what's going on at one location, and that makes it indeterminate to the second degree, right? Applying what we have illustrated previously. So we know that the structure is indeterminate to the second degree. We now have the question, which redundance do we want to choose? Obviously there will be two, but there are choices. So I am going to choose for redundance in my solution here. I'm going to change this fixed end for a rotor. When I go from a fixed end to that roller, I've eliminated the ability at this point to take a horizontal force, which I'll call my first redundant, and I've eliminated the possibility at this point to take a moment, which will be our second redundant. Therefore, the structure, these are the redundants and those are the positive directions. The primary structure, which is the structure without the loads and without the redundants, just to see it cleanly, it's this, right? So this is the primary structure. The criteria for the primary structure is that it must be statically determinate, right? No matter what the loading is, you could solve just using statics. And of course it must be stable, right? So this is our primary structure, which is what I see when I remove the redundants. That's the statically determinate basis. These are my two redundants, those are the directions, this is the problem. Of course, I haven't yet said what is the loading. So, let's say that the loading in this case that we're interested in is temperature. So, I'm going to take a look at this point and take a look at that cross section. So let's say that we look at the cross section AA. So if we were to cut like this and look up, let's say we would look at something like that. That means that column ED has that shape. It is B in width, and not to confuse with that D, let's say B bar in width and D bar in width, not BD. And D bar in depth. Okay? And what I am going to say is that, let's see, let me do it. I will erase this to make sure that things are clearer, okay? We've already made my point here. So if I look at section AA, enlarging it, I'm going to say that section AA is B bar by D bar, and that what we have is the following temperature distribution. So the temperature has increased by delta T on the outside of column DE, right? If I talk about outside being, this is the outside of the structure, the outside, and this is the inside for the purposes of discussion, right? So I'm saying on bar DE, the temperature has increased by delta T on the outside and no change has taken place on the inside. This is saying that something like if the sun, right, if there was radiation from the sun hitting the outside of the column there, right, then that side of the column which is receiving the sun radiation is heating up, and we are looking at a moment in time when the outside fibers have heated up by delta T while the inside fibers have not changed temperature. And we are assuming that the temperature distribution is uniformly linear within the depth. We want to know what are the moments, shears, stresses everywhere. We would like to know everything about what that is happening on the structure, about what that effect does to the structure. By the way, if the structure is statically determinate, previous lectures, before we started with indeterminate structures, we calculated deformations due to temperature, never calculated moments and shears and anything. Because in structures that are statically determinate, the changes in temperature do not induce any moments or shears because the structure is able to deform freely. Or I shouldn't say to deform freely, is able to accommodate the changes in shape that are demanded by the temperatures without the need for moments and shears appearing. In the case where the structure is statically indeterminate, this is no longer possible, and so in indeterminate structures, the appearance of a temperature change, in general, will lead to moments and shear diagrams. To make that even clearer, intuitively clear, before we go to this structure, allow me a small parenthesis. If we have a beam, and that beam, simply supported, right, received radiation from the sun on the top and got heated up, then the top fibers would get longer and the beam would tend to do this. We could calculate how much that is from our formulas, that integral of m1 phi p, when the phi p would be the curvature due to the temperature. But the beam would deform like that, but it would be free of stresses. Now, if the beam had been not not simply supported, but double fixed, right? Then it's obvious like that these angles that the simply supported beam takes when I heat it up cannot occur over here, right? And therefore, some moments would appear at the ends of this beam due to this heating to ensure that this condition is satisfied in the doubly fixed beam, and we would end up having moments here. So moments would appear, right, if we heat the top of this beam. So in the case of statically determinate, we do not produce any moments or shears. In the case of statically indeterminate, the temperature does produce moments and shears and axial forces and so on. Okay? Okay, so let's see, how can I best organize this stuff on such small board here? Because now we have to do quite a bit of, well, simple, but quite a bit statics. So what I'm going to say is this: we know the dimensions, right? L, L, and half of L. So I'm not going to crowd the drawing with those dimensions. L, L, half of L height. I am going to then say, let's see, that this is going to be my P sketch. No, I'm not going to be able to fit it, so I'm going to have to draw it a little bit smaller in order to keep them all on the sketch. So let me see. On this side, so this is going to be the primary structure with the temperature. That's the P sketch. Then we're going to have over here the primary structure again under the what? Under the x1 equal to 1 sketch, right? This marker is giving me a hard time. Let's see if this one cooperates a little better. So this is the x1 equal to 1 sketch. And then we will have finally this sketch here, which is going to be the x2 equal to 1 sketch. Okay? The p sketch, the x1 equal to 1 sketch, the x2 equal to 1 sketch. So since I selected my redundants, the x1 equal to 1 sketch is this, and the x2 equal to 1 sketch is this, right? Now I have to translate those temperatures into the p sketch. If there were loads, a uniform load here, a concentrated load or whatever, then we would do statics here and calculate our MP, right? And if we wanted to account for axial effects, we would also calculate our NP. And if we wanted to include shear effects, we would also have to calculate our VP. Now, in this case, we have, in the P sketch, nothing going on this bar. Nothing going on this bar. Nothing going on this bar. And everything is happening on this bar, on the right side column, because that is where the temperature change took place. Now, from before the erasing, remember that what I said that there was a temperature change, delta T, over bar, over this column, where this is the outside. That means that the strains over that cross-section are alpha delta T, where alpha is the coefficient of thermal expansion, right? The depth of that is d bar, right? Like this. Therefore, this angle right here is the curvature due to temperature. It's just the slope of the strain profile is alpha delta T divided by d bar, right? And we see also that in the neutral axis there is an average strain, and that would be our strain in the axial deformation direction due to temperature, and that axial strain is obviously alpha times delta T divided by 2. Okay? Now, I don't want to be carrying this symbol d bar because that's another dimension. So let's just say that the depth of the cross-section, we have a cross-section that is b bar by d bar, right? Let's say that d bar is 1/10 of L. So for example, if L was 10 feet, then this would be 5 feet, this would be 10 feet, and that would be a foot, right? It's kind of a little bit big, but that's what I used in the solution, okay? So d bar is 0.1 L. If d bar is 0.1 L, then we have that our temperature strain doesn't care. That's just alpha delta T over 2. But our temperature curvature can be seen to be 10 times 0.1 L, right? Alpha delta T divided by L. So we don't have to introduce any new dimensions. So I erase here. And I transplant my results to my sketch. And I say phi, which is the same thing as MP over EI, right? It's equal to 10 alpha delta T over L. And my E temperature here is alpha delta T divided by 2. They apply to this column. Everywhere else there is no curvature and there is no strain due to temperature, right? So I can erase this from here, give us our little bit of space, not much, but we have that. So that's our P sketch. Now, because there's going to be quite a few computations, as I said, they're all simple, but there's quite a few of them. In order to minimize the possibility of making an error, we will not eliminate the possibility, that's impossible, but we may reduce the possibility of making an error in signs. So it might be a good idea. We can always, as you know, as long as we are consistent, we can do whatever we want. But let's just go like this and say, if a moment gives compression on outside, we'll call it plus. So if a moment gives compression on the outside, we'll call it plus. That way, we don't have to, how should I say, especially because I don't have a sufficiently large board to work with. If you are on paper, you can always make your drawings clean and go back and take a look to see what was the sign convention that you used for a given bar. But here, I'm not going to have the luxury to continuously look back because I have to erase stuff. So what I will say simply, if a moment gives compressions on the outside, that's plus. That way I don't have to remember what I did on any particular bar. All my bars will be such that if the moment that I'm looking at produces compression on the outside, I'll call it plus. Okay? If I'm going to also look at axial here, so I will consider axial tension positive. So that way I know that now I don't have to take a look at previous drawings. Axial tension is positive. Moments that give compression on the outside are positive. Now we have to see, because even though we do not have moments in the PKs or axial forces, we have already the effect due to, if you had moment, it would give curvature. We have to decide what is the sign that we should give to that curvature and what is the sign that we should give to that axial temperature induced strain, given this convention. So again, remember that the temperature distribution over the column was like this, with alpha delta T, and this being a heating, right? That means that these fibers on the outside of the column got longer, right? So this is an extension, and therefore, since extension and axial tension are compatible, we conclude that our epsilon is a plus, according to the convention we chose. Now, the fact that there is extension on the outside means that in our column, the moments that we would be calling plus would be, the moments that would be needed to produce elongation on the outside would be like this, right? So those are the moments that would produce elongation on the outer fiber. Elongation on the outer fiber is the opposite of what I said I would use as plus, right? Because I said I'm going to continue, I'm going to use, in the column that was vertical, moments like that to be positive, right? To produce compression on the outside or shortening of the fibers. What I have here is lengthening of the fibers on the outside. So according to that convention, and you could certainly have flipped it, this is going to be a negative. So I have negative curvature and positive axial strain, again, based on that convention. If I wanted this to be a plus, I would just have to say moments on the inside are positive, right? All right. So I'm erasing that side, give ourselves room. And so this is how easy the completion of the P-sketch was, right? The P-sketch has been completed. Nothing, 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 and the temperature prescribed condition on this vertical bar on the right side. What do we have to do now? We have to solve for our unit and for our unit x2 equal to 1. So let's begin with our x1 equal to 1 here. I will do the statics, and then after this completed, I'll transform the results, I'll transplant the results here, I'll erase. Oh, I'm sorry, this is not like this, this is a roller, right? This is a roller. So I remove the I remove the horizontal reaction and the moment. So now, first we take a look at this bubble. Go through the hinge, turn around, grab the support, and go like this, right? So I have the hinge, go like this, go like this. At this point, we have the horizontal reaction of 1. There's nothing else here except perhaps a reaction. So it's going to be a reaction maybe like this. And then at the hinge there is no moment, but there could be a force, axial, and there could be a shear. Now summing moments, this distance I'm not going to draw because I told you, let's just remember, right? This distance full is half of L. This distance to the hinge is L. So we have 1 times half of L counterclockwise equal to watt times L. Shows me that this is 0.5. Summing forces in the vertical direction shows me that this force is 0.5. Summing forces in the horizontal direction shows me that that force is 1. Right? Now in your paper you don't need to be so frugal with writing equations. So write them down. Sum of the forces of the moments about 0.0 equal to 0, blah blah blah. Therefore this is this much, and so on. Right? Sum of the forces in the y direction equal to 0, therefore this, and so on. Now that we have that, what else do we need? We can have our other half, right? And from the hinge to the left, I'm sorry, let me try to keep the scale more or less correct. It's actually longer from the hinge to the left than down. So this reaction gets transplanted downward as 0.5. This one, which was to the left, gets transplanted to the right as 1. There is no moment there. Here, it's quite obvious. Well, actually, I shouldn't say quite obvious. There's 3 reactions here, right? Because it's a fixed end. So there is a vertical, which from sum of the forces in y is obviously 0.5. There is a horizontal, which from sum of the forces in the x direction equal to 0 is obviously is obviously 1. And then summing moments about this point, and let me write that equation. So if I call that M, A, I could say minus MA plus 0.5 times L plus 1 times 0.5 L is equal to 0, right? Therefore, 0.5 L plus 0.5 L is L. That goes to the other side with a different sign, and we get that the moment MA is equal to 1 L, right? And so we find that. So now we have that free body, this free body, and we have found the reactions. I guess I just don't need to do that anymore. Just write it like that, okay? So we have the 2 free body diagrams of the 2 halves from the hinge to the right, from the hinge to the left. Okay, now what? We need the moments and the axial forces, right? So our first free body diagram will be this one. That's my first bubble. I need a coordinate, right? So I'm going to establish that something that starts here and moves up, has a 0 at that level, is going to be called y. Therefore, that bubble looks like this. There is a force of 1. There is a reaction downward at 0.5. There is a distance y to that point. And now, do I have to decide what is which direction I put the moment? No, I already made up my mind, right? I said that my moment is going to be always assumed so that it gives compression on the outside. So if you look, if that is confusing to you, just take a ruler. I hope it's not, but I think we did that quite a few times before when we were dealing with the beams. You know, you take a bar, you go like this, you should see that that moment is producing compression on the outside, right? So this is our sign convention for the moment M1. So sum of the forces in X, this is a 1 here. Sum of the forces in Y gives me my N1, which is going to be 0.5. And then from the moments, I can see that M1, summing moments about here, M1 minus 1 times Y is equal to 0, right? So I find that the moment here, M1 is Y, and the axial force over this bar, is it tension or compression? Is tension, and we agreed to call tension positive so we don't have to keep looking back. And so we have that over that bar, the moment is Y, and the axial force is 0.5 on this sketch. So we'll come here and we'll say, here the moment is Y, and the axial force is 0.5, right? Now, we go to this bar. Now, how do you do that bar? You can do it any way you want. You can do this bar any way you want. You could take the bubble from here and call a distance x to the right, and that'd be perfectly fine. I'm going to switch the game just a little bit for interest or whatever, and I'm going to just start a coordinate there that moves to the right instead of going that way to the left. So if I start a coordinate at the hinge that moves to the right and call it x, then I can use this as my bubble. And I see that that bubble would look like this. It has 0.5 up there. It has 1 to the left. Over here I have a shear, which obviously is in that direction. I have an axial, which is obviously in this direction. And I have a moment. Which is the sign convention for the moment? Well, we said we will take the moment to be positive when it produces compression on the outside, and that would be the sign convention consistent with that argument. Therefore, I would then say, since the distance from here to here is x, that summing moments about this point minus m1 plus 0.5x is equal to 0, or m1 is 0.5x, right? And from sum of the forces in the horizontal direction, we would find that n1 is 1, and it's positive because what? Because it's tension. And we agreed to call tension positive. So I transplant my results over here. I say on this bar, m1 is 0.5x, n1 is 1. And so I'm done with that half. Then I erase here. I don't need that anymore. I don't actually need this half anymore either. So I take that out of the way and we focus on what's going on this part, which is to complete my other half. So I'm going to start, before I do that, I have a coordinate y. I just decided to use something that goes from here to the right and call it x. I'm going to start something that goes the other way here and call it z. So that means that over here, I'll start something z this way. My bubble is this, and so I have this 0.5, 1. This is the point where I cut, not the hinge. This is my bubble, right? So at this point, sum of the forces in x, that's obviously 1. Sum of the shears, that's obviously a half. And which sign convention do I need? Well, at this cut, I need to take the moment like this, right? Because that's what I'm using to keep myself straight. So I don't have to look again to see which direction did I assume. That's the moment that produces compression on the top, and so that's my M1. So I say M1, summing moments about this point, plus 0.5 times this distance, which would be z, is equal to 0. And so we conclude that M1 is minus 0.5 z. And that N1 is tension is equal to 1. So we come here and we say on this bar, M1 is equal to minus 0.5 z, and n1 is equal to 1. Okay? We're done here, here, and here. We have one bar left. That bar is this part here. So I don't really care about this right now. So what I'm going to do now is to take this bubble. Why? Because I already selected a coordinate that is at this level moving up as y, so I can still call this y and it would be legal, right? So I can say that that part has a moment L, has an axial of 0.5, has a shear of how much? No, it has a horizontal. Obviously the horizontal had to be 1. I erased it a little too soon or didn't put it. But it has to be 1, because I can see from the sketch that's the only other horizontal, right? And so here we have our cut, and so there is a shear, which will have to be 1. There is an axial that'll have to be a half in that direction. And there's going to have to be a moment. Now the distance from here to here is y. And we're going to have to assume some sign for the moment, but we already decided. Our moment is selected such that it produces compression on the outside. And so that's M1. If I look at that bar, I go like this, I put compression on the outer fibers. And so I say minus M1, summing moments about here. Minus M1 minus L plus 1 times y is equal to 0. Therefore, M1 is equal to y minus L, right? So M1 is equal to y minus L. And from the sum of the forces in the y direction, we find that N1 is minus a half. Why is it minus? Because it is compression, and we agreed, that tension was going to be called plus. So I transplant the results to here, and we have M1 is equal to y minus L, and M1 is equal to minus 1/2. Okay, so that has concluded our work on the x1 equal to 1 sketch. We can erase the right side of the board, give ourselves room to work with the other one. Okay, so the same routine, except we're now doing the x2 equal to 1 sketch. So we take the free body diagram from the hinge to the right. That's L, that's half of L. We have a moment of 1. Here we have potentially a reaction. We're going to sum moments about here. There is no horizontal, right? It's a roller and there's nothing there. The x1 equal to 1 was here. So if we sum moments, I can see right away that this is going to be in this direction. So summing moments about here, I get minus, let's call it r if you'd like to go through it. So it would be summing moments about O. There's going to have to be something here and no horizontal. It's going to be minus 1 plus r times this distance, which is L equal to 0. And so from there you see that r is 1 over L, right? So we conclude that r is 1 over L from that sketch. Therefore, we find that in this schematic, this is 1 over L. That is the 1 kip, not 1 kip, 1 kip foot moment. And summing verticals, this will be 1 over L, and summing horizontals, that will be 0. So those are the reactions on that support. We go to the other support, and we find something like this. That 1 over L gets transplanted in the other direction. the horizontal is 0. Here there are in principle 3 reactions because this is a fixed end that has been eliminated. Summing forces in the y direction, obviously that's 1 over L. Summing forces in the horizontal direction, obviously this is 0. And now summing moments about this point, 1 over L times L is clockwise, so it's clear that 1 over L times L is 1, and so there must be a moment of 1 in the counterclockwise direction for the body to be in equilibrium. And so we now have the reactions. The reaction on the right hand side is 1 over L downward. The reactions on the right hand side is 1 over L upwards. And there is a moment here which is not a reaction, is the applied 1 kip foot. And there is a moment which is a reaction on the right side, which is a 1 kip foot in the same orientation. Okay, so we have the reactions. Now we begin our process of cuts to get what are the internal forces. So beginning on the right hand side, this is our first bubble, right? So here is the cut. It has a load of 1 over L going downward and a moment like this of 1. What kind of directions must we assume here? We don't have to look back because we know we assumed that the moment was producing compression on the inside. From summing forces in the horizontal direction, it's clear that there is no shear here and that there is an axial of 1 over L. And as far as the moment is concerned, we can say minus M1, right? I'm sorry, minus M1 minus 1 and nothing else equal to 0. Therefore, M1 is minus 1, right? And N1 is 1 over L positive because it's tension. So we now have completed for this bar, and so we write right here, N1 is minus 1, and N1 is 1 divided by L. And so we've completed the vertical column on the left side. We must now do this part, right? I will erase here. From this side, we've already decided that our coordinate is x, right? It's starting like that, so my bubble is this. I see this horizontal piece here with 1 over L going up, nothing like this. Therefore, there is 1 over L going like that. This distance from here to here is what am I? Yeah. No, not z, x. This distance from here to here is x because I'm starting at the hinge, right? This is the hinge. So this is my 1 over L and 0, my distance x. My sign convention for the moment here must be that way in order for it to be compression on the top, so I don't have to remember. So I have something like this, and this is my M1. And so I have nothing horizontal here. And so summing moments, I get minus M1 plus x times 1 over L is equal to 0. And therefore M1 is x over L. So we go to this bar and we say over here M1 is x over L, positive, and N1 is 0. Right? And we've done half the structure on that side. So we can erase all of this. Well, actually, no, I could have saved this side. Yeah, I will. We still have this second part here, right? So from this bubble, cutting from the hinge to the left, we have something like this. It's too wet. Whoa, nothing. Give me a second. Okay. So we've done this part. We're looking from the hinge to the left here. So we have 1 over L, which is that force, no axials, and we just cut over here. That's going to, and that distance from here to here is Z, as we've seen from this sketch. Our moment convention is necessarily this, and there is no axials, right? So summing moments, I get M1 plus 1 over L times Z, it's positive, equal to 0. So we find that M1 is minus Z over L, right? So we transplant to here, and we have M1 is equal to minus Z over L, and N1 is 0. And we have 1 bar left, and that 1 bar left is the left side column. And that left side column, we've already seen how we take that free body of that bubble, right? We do this, and from that free body we get something. Well, no, these ones are giving out on me, and I have to find out how to go buy some. Hold it a second. Actually, let me stop here and start again, just to fraction the length of the video.